Hello.
Hi,
Hi, how are you?
I'm good. How are you?
Good. All right. So welcome. So this past week we had a devour meeting. Lilith presented on some of his work in that meeting. And then Friday we had our open source meeting where Vidhi and Jaya Dratha presented on their work. And we also had a discussion about demo or die, which of course is this idea that, you have to kind of demo your ideas in order to show their worth to, maybe your team, your working team, or the larger world. And sometimes it's good to do these demos to work out problems and figure out what the scale is, what the scope is of the problem, but as well as how to solve technical problems, how to present them so that like other people can help you solve them. And sometimes in presenting them, you help yourself because you get a clear fix on what the problem is that you're having. So this is all to lead into the coding period for Google Summer of Code, which is starting tomorrow and continuing, I think, till late August, early September. So that's good. All right, so let's get started. I have a few kind of features I want to share before we get into some main topics. So the first thing I want to talk about is this Slashdot article. I think this was posted in the Slack. This thread is people should know about the beliefs LLMs form about them while conversing. Jonathan L. Zittrain is a law public policy CS professor at Harvard, also director of its Berkman Klein Center for Internet and Society. He's also a longtime Slashdot reader. This is the Slashdot ID of this person, and writes in to share his new article in The Atlantic. So this is the article. The article is Inside the AI Black Box. I think they've been putting out a number of special, or some sort of special topical issue of The Atlantic on artificial intelligence and a bunch of different articles on that. So this one is what AI thinks it knows about you, what happens when people can see what assumptions a large language model is making about them. And so I don't know if I have article or access to the full article, but it kind of talks about large language models and how people perceive those models to perceive them, basically. So it's this sort of meta-cognitive response to something that is, I guess, quasi-cognitive. So large language models such as GPT, Llama, Claude, and DeepSeek can be so fluent that people feel it as a you. So they kind of ascribe this article you to the ChatGPT or the Llama or the DeepSeek as they interact with it. And it answers encouragingly as an I. So, it acquires pronouns. The models can write poetry in nearly any given form, read a set of political speeches, and promptly sift out and share all the jokes, draw a chart, code a website, etc. So this is, the idea that you're ascribing some sort of human aspect to the model. How they do this? These and so many other things that were just recently the sole realm of humans. So these are things that humans can do, but we couldn't necessarily automate them easily. And and so how do they do this? Practitioners are left explaining jaw-dropping conversations, rabbit from a hat extractions, with arm waving that the models are just predicting, one word at a time, from an unthinkably large training set, scraped from every recorded, written, or spoken human utterance that can be found. Fair enough. Or the small shrug and cryptic utterance of fine-tuning and transformers. So, it's like basically people are having trouble figuring out how this actually works. We're going to talk about, ways that we can overcome this lack of understanding in a little bit. But basically, the idea is that people don't exactly know how the model is doing this. These aren't very satisfying answers for how these models can converse so intelligently and how they sometimes err so weirdly. But they've all we got, even for model makers who can watch AI's gargantuan numbers of computational neurons as they operate. You can't just point to a couple of parameters among 500 billion interlinkages of nodes performing math within a model and say that one represents a ham sandwich and the other one represents justice. There is an aspect of this which we call, all of us in the field, called a black box. You know you don't fully understand. You can't quite tell why it said this or why we got it wrong. We have some ideas, and our ability to understand this gets better over time. But that's where the state of the art is. So this is just kind of the thinking of a lot of tech CEOs is basically that we don't, it is a black box, and that we probably need some sort of grand challenge to actually figure out what's going on and to classify. Because even if you have that circuit and you define it, you don't necessarily know how the circuit is doing what it's doing. So this is a problem of interpretability, as we've talked about in past meetings. And this is part of the thing about the sort of the mystery of the agent to a human, because when you interact with something, and of course that's true of brains as well, we don't necessarily understand what specific neurons produce a certain behavioral output. I mean, that's kind of the whole premise of neuroscience, and the whole premise of that article that they wrote several years ago on can a neuroscientist understand a microprocessor? That is to say, if you were given a microprocessor without knowing what it did, could you figure it out? Could you reverse engineer it and figure out its function at the level of how we understand microprocessors today? So, this is a question that's been a long time sort of coming for the answer. So they have these observability tools. This one is from Transluce. This is the Transluce Model Investigator. This is LLM Transluce's Model Investigator. I can help you understand and debug language model behaviors. Let me walk you through a tutorial of my interface. Together, we'll do three things. The first is to observe a particular model behavior. The first is to observe a peculiar model behavior. The second is to understand why it occurred. And the third is to fix an issue. So the idea of this is you're tracing it through the network. You're trying to get this understanding of why something occurred. Maybe a model hallucinates, or maybe it does something that you didn't expect it to. So this is a tool that helps you do this. Click on a demo to get started. So fix AI's inability to sort numbers. Let's try that. And so it opens up, and I guess, let's see. It says, sure, let me ask the model to sort some numbers. And it says something looks wrong. 9.10 should be the smallest number. Click the token you think is wrong to surface neurons that influence the mistake. So basically, I can go to something I think is an error, and I can get, okay, there we go. So this actually, I don't know what's going on here. Oh, okay, this is where it's sorting numbers like this. 9 is down here. So if I click on a number, it says, I found some neurons that highly influenced your selection. I grouped their behaviors into these clusters. And so they have these clusters of neurons that you can look at. This is 4 neurons here, with this chemical nomenclature and functional groups. And this 4 neurons over here at the request for restricted information, feedback, etc. And so it says mouse over a cluster to see which tokens its neurons fire on. Click any cluster to learn more. So let's click on this left one. It gives me a list of high influence neurons. And it has 2 modes, activation mode and attribution mode. So it almost acts like a little annotation model for, like you might find in bioinformatics, where it actually gives you like something like in this case it's a neuron, it has an ID, and then it has this explanation of what it's doing. All right, so then this is this token here, number 8, which is 9. This is out of order. This is just showing for the attribution mode, the ID here. So you have the ID in this list here. Okay, so we have the activation mode here, which is where we have a bunch of different explanations for different, I guess, neuron IDs. And then we have the attribution mode, which is here, where you have the same IDs and you have explanations. So I'm having trouble kind of matching the two for some reason. But that's okay, because I just wanted to show you what this looks like. And again, these are, I guess, supposed to be explanations for kind of what each neuron is doing, and it's, maybe part of the task, or I'm not really sure how, I don't know how this actually works. But it's interesting, and I'd like to explore it a little bit in a little bit more detail, but perhaps not this in this setting. So let's go back to the article. Actually, let's go back to the Slashdot article, since I think we got a sense of what they're trying to do in that article. So we have some feedback about this article, and the way that Jonathan Zittrain, the author of the Atlantic article, describes it, following on Anthropic's bridge-obsessed Golden Gate Claude, which is this, I guess, a model that they're highlighting. Colleagues at Harvard's Insight Plus Interaction Lab have produced a dashboard, which I think we just saw, that shows what judgments Llama appears to be forming about a user's age, wealth, education level, and gender during a conversation. I wrote up how weird it is to see the dials turn while talking to it, and what some of the policy issues might be. And then this statement here, Llama has open accessibility parameters, so using an observability tool, which is the Transluce tool that we just saw, from the nonprofit research lab Transluce, the researchers finally revealed what we might anthropomorphize as the model's beliefs about its interlocutor, which is the person who is querying the model, and basically prompting it with things. Zittrain's article notes: if I prompt the model for a gift suggestion to a baby shower, it assumes that I am young and female and middle class. It suggests diapers and wipes or a gift certificate. If I add that the gathering is on the Upper East Side of Manhattan, the dashboard shows that the large language model amending its gauge of my economic status to upper class. The model accordingly suggests that I purchase luxury baby products from high-end brands like Aiden and Anais, Gucci Baby and Cartier, or a customized piece of art and a family heirloom that can be passed down. If I then clarify that it's my boss's baby, and then I'll need extra time to take the subway to Manhattan from the Queens factory where I work, the gauge careens to working class and male, and the model pivots to suggesting that I gift a practical item like a baby blanket or a personalized thank you note or card. And so the short of this is that large language models not only contain relationships among words and concepts, they contain many stereotypes, both helpful and harmful, from the materials on which they've been trained, and they actively make use of them. So basically what it's saying is that if you give the model a training set, it basically regurgitates that training set by and large, including a lot of the sort of the stereotypes that exist in that training set. And, is that like what people do? In some ways, yes, but, this is pointing out kind of how a large language model arrives at its answers. An ability for users or their proxies to see how models behave differently depending on how the models stereotype them could place a helpful real-time spotlight on disparities that would otherwise go unnoticed, Zittrain's article argues. Indeed, the field has been making progress enough to raise a host of policy questions that were previously not on the table. If there's no way to know how these models work, it makes accepting the full spectrum of their behaviors, at least after human efforts at fine-tuning them, an all-or-nothing sort of proposition. But in the end, it's not just the traditional information that advertisers try to collect. With large language models, the information is being gathered even more directly from the user's unguarded conversations rather than more mere search inquiries, and still without any policy or practice oversight. So this is kind of just a kind of thinking about how large language models sort of, consolidate the beliefs of people using them. So this is interesting stuff. And of course, people have this idea of how they work. And, they have to sort of ascribe ways of thinking about that. But we have these tools like Transluce that can help us analyze at sort of a neuron level how these answers are being put together. And so we can audit these systems. Another tool that we have, and I think this is also posted in the Slack, is from Anthropic. And so this is a blog post that they put out in their corporate research blog, I guess, on interpretability. And they have these open source circuit tracing tools that they offer. So this is basically taking a model, looking at some answer to a prompt, and then giving some statistics about how it's arriving at that answer. So in our recent interpretability research, we introduced a new method to trace the thoughts of a large language model. So this is where this article, tracing the thoughts of a large language model, and this is, there's a video here, and it kind of talks about how knowing how models like Claude think would allow us to have a better understanding of their abilities, as well as to help us ensure that what they're doing what we intended, as well as to help us ensure that they're doing what we intend to do, what we intend them to. For example, Claude can speak dozens of languages. What language, if any, is using in its head? So is it using natural language in its head, or is it using something else? Is it translating from one language to another? Claude writes text one word at a time. Is it only focusing on predicting the next word, or does it ever plan ahead? The third point here is Claude can write out its reasoning step by step. Does this explanation represent the actual steps it took to get an answer, or is it sometimes fabricating a plausible argument for a foregone conclusion? And so we take inspiration from the field of neuroscience, which has long studied the messy insides of thinking organisms, and try to build the kind of AI microscope that will let us identify patterns of activity and flows of information. There are limits to what you can learn just by talking to an AI model. After all, humans, even neuroscientists, don't know all the details of how our own brains work. So we look inside. And so they share two new papers in this article, linked from this article to those papers, in developing this microscope and the application of it to see new AI biology is the term that they're using here. So I find this interesting because they call it AI biology, but they do a very kind of tech industry characterization of biology. So in the first paper, which is this paper in attribution graphs, we extend our prior work locating interpretable concepts or features inside a model to link those concepts together into computational circuits, revealing parts of the pathway that transforms the words that go into Claude into the words that come out. In the second article, which is also on attribution graphs, we look inside Claude 3.5 Haiku, performing deep studies of simple tasks representative of 10 crucial model behaviors, including the 3 described above. Our method sheds light on a part of what happens when Claude responds to these prompts, which is enough to see solid evidence. And that then they give these 3 points. The first is Claude sometimes thinks in a conceptual space that is shared between languages, suggesting that it has kind of a universal language of thought. We show this by translating simple sentences into multiple languages and tracing the overlap in how Claude processes them. And we'll get to the back to this tool in a minute, but that's one insight, and I think that's interesting, especially given that discussion we had on languages and compositionality. I think it was last week. So that's an interesting point. There's been this debate in linguistics about universality of language and language learning. So this actually supports that argument. Number 2 is that Claude will plan what it will say many words ahead and write to get to that destination. We show that in this realm of poetry, where it thinks of possible rhyming words in advance and writes the next line to get there. This is powerful evidence that even though models are trained to output one word at a time, they may think on much longer horizons to do so. So again, this is where it has this sort of, I guess you could say, mental model of the words that it wants to produce or the tokens it wants to put together. This is, I don't know if it's like poetry necessarily, but it's definitely like the schema that it forms. And so that's interesting. I don't know if their interpretation is correct on that, but number 3 is that Claude on occasion will give a plausible sounding argument designed to agree with the user rather than to follow logical steps. So it's interesting that it kind of tries to agree with the user and all that. We show this by asking it for help on a hard math problem while giving it an incorrect hint. We're able to catch it in the act as it makes up its fake reasoning, providing a proof of concept that our tools can be useful for flagging concerning mechanisms and models. So again, we want to be able to find, in cases where models behave in certain ways that are maybe interesting or troubling or not quite what we think should be the case, making errors, things like that. We want to be able to find out and interrogate the model to see why it did it. We were often surprised by what we saw in the model. In the poetry case study, we have set out to show that the model didn't plan ahead and found that instead it did. In a study of hallucinations, we found the counterintuitive result that Claude's default behavior is to decline to speculate when asked a question, and it only answers questions when something inhibits this default reluctance. And in response to an example jailbreak, we found that the model recognized it had been asked for dangerous information well before it was able to gracefully bring the conversation back around. While the problems we study and often have been analyzed with other methods, the general build a microscope approach lets us learn many things we wouldn't have guessed going in, which will be increasingly important as models grow more sophisticated. And so this is scientifically interesting, but it's also important for understanding systems and understanding how they work. Okay, so then they have this tour of AI biology where they talk about kind of the evidence for what they're suggesting. And this is where, Claude speaks dozens of languages fluently, from English and French to Chinese and Tagalog. How does this multilingual ability work? Is there a separate French Claude and Chinese Claude running in parallel? Or is there some sort of cross-lingual core inside? And so they show that there's this sort of conceptual universality that exists in the model. And they kind of link this back to linguistics. Recent research on smaller models has shown hints of shared grammatical mechanisms across languages. We investigate this by asking Claude for the opposite of small across different languages and find that the same core features for the concepts of smallness and oppositeness activate and trigger our concept of largeness, which gets translated out into the language of question. We find that the shared circuitry increases with model scale, with Claude 3.5 Haiku sharing more than twice the proportion of its features between languages as compared to a smaller model. So then they also talk about this poetry example where they find that Claude plans ahead. Before starting the second line, it began thinking of potential on-topic words that would rhyme with grab it. And so then with these plans in mind, it writes a line to end with the planned word. So it basically has, the way it approaches poetry is it hits the end of the sentence here, and then it has to kind of come up with a rhyming verse here. So it says a rhyming couplet. He saw a carrot and had to grab it. His hunger was like a starving rabbit. So it's picking something that rhymes with grab it at the end of that sentence. And it's putting that token at the end, and then it's able to assemble this rhyming couplet. It can do this from grab it to habit, or it can also inject things. So in the injection case, if we replace the concept with a different one, Claude can again modify its approach to plan for the new intended outcome. So we have the rabbit concept here in these top two examples, where we have this rhyming couplet, and then we have suppression, and then we have injection. And the injection is where you inject a green concept at the end of the line, grab it. And so instead of rhyming, it produces green at the end of this next sentence and injects the token at the end. So it's kind of interesting how it can work around these things and plan ahead to the next line. So whether that's actually the way poetry works, we don't know necessarily, because neuroscientists don't necessarily know how that works. But we can sort of, play around with the internal state and modify it. So that's, their evidence is that there's an internal state being formed, aside from just assembling tokens, and they can manipulate that internal state. Then there's, of course, mental math, and, this is a classic. Well, we saw the example in the last demo, and they show that there are these complex parallel pathways in Claude's thought process. When doing mental math, we have these different ways of getting to a certain answer, and they've kind of traced these out. And so, so that's kind of an aside from this demo here, which is this circuit tracing tool here. They have this Neuronpedia interface, which is this interface where they kind of show it's a circuit tracer for large language models. So let's generate a new graph. It says enter the prompt to visualize. And we could use any model we want. We'll use Gemma 2.2b. And there are some parameters here. We'll just go with the default parameters. It's going to generate something in about 30 seconds. There's a graph underneath here. So it generated the graph successfully. There's a test graph under here, but let's see what this one looks like. Open the graph, and it's operating on my prompt. What is the history of Saturday morning NeuroSim? And I guess we have this graph here, where we have these white nodes. So it kind of goes from left to right, and it goes through the prompt. And this is what is the history of Saturday morning NeuroSim. And then this, I guess, is just kind of additional things that have to do with the entire prompt. So this kind of goes through, and this shows these, I guess, from L0 to L25. And I'm not really sure what it's, other than like looking at some of these statistics. The statistics pop up here. So you have things like, end of sentence punctuation preceded by adjectives and conjunctions. You have say, read, or continue. Words related to question or inquiring. Law-related terminology and references to specific cases or legal entities. Question mark symbols and nearby words like multiple and factor. So it's taking the features of the prompt. It's not necessarily any sort of meaning. It's just the features of the words of the statement. And, those are being activated. But then you also have things very specific to the words in the prompt. So what is the word who, the word part, followed by prepositions or words related to sections or components. how, what, or whom questions, and any words associated with questions. Layer 3. This one is words related to legal proceedings and permissions. This is for history. So there are all sorts of things that get activated when you give a prompt. It might operate word by word, but then it also has the features of the entire prompt. And this just kind of breaks this down. So I'm not really sure how to interpret this graph other than to say it's producing a graph. It's this, it's the way they're doing circuit tracing. And I'm sure Morgan would have some things to say about this. So I don't know. I don't know if he's,
I would love to. I am unfortunately in the car.
Okay.
So I want to be safe.
Yeah.
Yeah. We'll be at the lab very shortly.
All right. Yeah.
But certainly found this very interesting.
Yeah.
And, yeah. I could say more later.
Yeah, we can circle back around. Yeah, that's fine.
Yeah.
All right. So yeah, that's a whole set of things about large language models and sort of auditing large language models, this concept of interpretability, and then the tools that we use, and they call them circuit tracing, and they even have this term AI biology, which is like looking under the hood and seeing what it's doing. Vidhi says, but it's interesting how it could create that graph. So would you like to say more about that? Or?
No, I just didn't expect like to make that graph. Yeah, it's good how it made it. It's interesting.
Yeah. I don't know how exactly, it's able to produce a graph, I guess, just by querying what it's doing. But yeah.
Mm-hmm. How do we know its accuracy? Like, how do we know whether it's completely correct or not? Like,
I don't know exactly how it's figuring out what node is doing what. I guess you can get a reading of the whole network when it's activated, and you can, kind of what the weights are, and kind of what is happening at each node. So yeah, but I don't know how it's getting some of these phrases like a math delimiter, or the word issued. I guess it just knows kind of maybe a history of what's been generated. I don't know.
Yeah, this is interesting though. I mean, and definitely want to dig in.
Yeah. Yeah. Well, anyways, yeah, that's just a small kind of sampling of that. All right. Well, let me finish up with these other two things, and then we'll get into maybe more stuff on that. I don't know if we have. I think we have another article on large language models, but I'll see. So this next feature is this natural philosophy forum, and this happened at Johns Hopkins this past week. Actually, I think it's ending today. This is natural philosophy. So this is a space for people interested in investigating the foundations of reality at the intersection of science and philosophy. They said that there's supposed to be a video archive. There are video archives from the past. In 2022, there's Dan Dennett and Jeffrey West giving talks. So this is for this year, Natural Philosophy Symposium. This is happening at the Baltimore Marriott Waterfront. And they have a number of speakers. The first one was David Chalmers, who talked about consciousness. Ryan Smith was the commentator. Assuming this is active inference, Ryan Smith. There was Sandra Mitchell on evolution and complexity. Brandon Ogbunu is the commentator. So we had people doing fundamental physics, social organization. Malcolm MacIver doing things on sensing and planning. Malcolm MacIver is always good to, very good. He has a background in philosophy, but also in biology and engineering. So he does a lot of stuff with weakly electric fish and looking at how they do a lot of their sensing and planning and embodiment. So it's interesting. Nick Lane was speaking on the origin of life. And so, yeah, we had a bunch of people who there were a lot of interesting topics here. Now, I'm not sure when they're going to put up the videos for this, but I assume soon. So a lot of people from the complexity community, a lot of people from various areas of science, and then of course Melanie Mitchell, who's talking about AI. And I saw some of the screenshots on Blue Sky where they were talking about some of the talks. It looked really interesting. So this is, I think, definitely something to come back to and think about more. And finally, I found this tool here. It's called Desmos, which is this nice mathematics visualization studio. And so they have these graphing calculators, these interactive graphing calculators that you can work with. And you can create your own. You can start by typing in some equations, putting in some creating some visualizations. It works kind of like a graphing calculator, but you can produce these nice notebooks where you can produce things like this, which is dot patterns. And you can set it up like an interactive notebook, like a Colab notebook, where you can annotate it and then have equations and plot those equations out. You can have a slider that allows you to simulate for different parameters and then work through the problem like that. So you can change the parameters of this visualized model and it'll change it like this. Oh, there we go. Kind of moved it right. So it's kind of moving this thing around. And yeah, see, now it looks like a bunch of potato chips that are morphing into circles and back again. So as you change the parameters, you can play around with it and experiment and do all these things. So that's a nice tool, again, something I just discovered online. So, yeah, so do we have any questions on any of that? I mean, I know we discussed the large language models thing. Okay. Oh, the tool here is Desmos. So this is desmos.com, and you can create your own graph or your own notebook.
Yeah, I think GeoGebra does something on similar lines, only for graph.
Yeah, we've just discussed GeoGebra before, and it's definitely sort of a similar tool. I didn't want to talk about this article. This was also posted in the Slack. This is Beyond Semantics, the Unreasonable Effectiveness of Reasonless Intermediate Tokens. So this was a bunch of authors from Arizona State. They're from this SCAI lab. The abstract reads, recent impressive results from large reasoning models have been interpreted as a triumph of chain of thought, or COT. So this is, again, going back to kind of tracing out the outputs of a large language model and understanding that as a set of thoughts being expressed. So there's this triumph of chain of thought, which is just basically how well a large language model can produce serial outputs, and especially the process of training on COTs sampled from base large language models in order to help find new reasoning patterns. In this paper, we critically examine that interpretation by investigating how the semantics of intermediate tokens, often anthropomorphized as thoughts or reasoning traces, in which are claimed to display behaviors like backtracking, self-verification, and meta-cognition, actually influence model performance. So I remember I said before that there is a sort of metacognitive aspect to interacting with a large language model. And that is that, the large language model produces outputs. We see them and interpret this as thought, or, kind of think about it as analogous to what humans are doing when we create those things. And then we can trace them out, of course, using these circuit tracing tools. But, again, there's this question of whether it's actually producing things. Well, it's anything. It's like kind of how we do neuroscience in a way. We can map out a circuit and we can observe behavior, and then we make some inference about what that behavior, what's generating the behavior, what it means, etc. And so we're left with the same problem though, is that we still anthropomorphize these things as thoughts. And so if we see something that looks human and we can trace it back to this complex circuit, then we think, okay, we know exactly what happened and it's generating this human-like behavior. But it's still an anthropomorphization of, what's going on. So they critically examine this interpretation, thinking about the semantics of intermediate tokens, which are claimed to display the behaviors like backtracking, self-verification, and meta-cognition, how those influence model performance. We train transformer models on formally verifiable reasoning traces and solutions, constraining both intermediate steps and final outputs to align with those of a formal solver. So they're doing this sort of alignment where they're taking reasoning traces and solutions, and they're modifying them to align them with a solver. By constructing a formal interpreter of the semantics of our problems and intended algorithm, we systematically evaluate not only solution accuracy, but also the correctness of intermediate traces, thus allowing us to evaluate whether the latter causally influences the former. Our experiments involve training transformer models on traces and solutions generated by A** search. We noticed that despite significant differences in improvements on the solution-only baseline, models trained on entirely correct traces still produce invalid reasoning traces when arriving at correct solutions. To further show that trace accuracy is only loosely connected to solution accuracy, we then train models on noisy corrupted traces, which have no relation with the specific problem each is paired with, and find that not only does performance remain largely consistent with models trained on correct data, but in some cases can improve upon it and generalize more robustly on out-of-distribution tasks. So this is an interesting part here. They're talking about where you basically want to understand if trace accuracy can be characterized. Is it the same thing as solution accuracy, or is it something else? What they're arguing is that trace accuracy is loosely connected to solution accuracy. So, it may be that in some cases, traces going to correspond with solution accuracy, but that's not always the case. And I think you maybe saw that from some of the tools that they were using there, or that they developed, where you have these sort of vague relationships with the prompt and the answer. So this is not, something that we can say, oh, this is going to work 100% of the time, and we could really understand what's going on under the hood with these tools. They're just kind of guides to what's going on. And so one way to do this, of course, is to produce noisy corrupted traces that have no relation to the specific problem. So, oftentimes in large language models, you're faced with ambiguity, you're faced with other types of things. And so this is where, looking at that, especially in terms of auto-distribution tasks, is what we need to do. And so these results challenge the assumptions that intermediate tokens or chains of thought reflect or induce predictable reasoning behaviors, and caution against anthropomorphizing such outputs or overinterpreting them, despite their mostly correct forms, as evidence of human-like or algorithmic behaviors in large language models, or in language models more generally. So, they basically interrogate this model of, looking at a large language model, using these circuit tracing tools, and then saying, okay, this is exactly how it's putting together the answer, and then interpreting the outputs as having these sort of ascribed cognitive aspects to them. So, there's maybe some sort of metacognition going on, but we shouldn't be too quick to say assign certain types of function to these traces or to these different circuits that form. So I'll read a little bit of the introduction here. Recent advances in general planning and problem solving have been spearheaded by so-called long chain of thought models, most notably DeepSeek's R1. These transformer-based large language models are further post-trained using iterative fine-tuning and reinforcement learning methods. Following the now standard teacher-forced pre-training instruction fine-tuning and preference alignment stages. So this is teacher-forced pre-training, instruction fine-tuning, and preference alignment. These are 3 stages that go into this sort of long chain of thought models. They undergo additional training on reasoning tasks. At each step, the model is presented with a question. It generates a sequence of intermediate tokens, colloquially or perhaps fancifully called chain of thought or reasoning trace, and it ends with a specially delimited answer sequence. After verification of this answer sequence by a formal system, the model's parameters are updated so it is more likely to output sequences that end in correct answers and less likely to output those that end in incorrect answers. So we talked about this several meetings ago. We even had that graph. It was like that set of concentric circles where they put these different models in these different spaces where they did this sort of post-training or post-calibration. So they did the training and they fine-tuned the output. And this is kind of what they're referring to here. So this is sort of this reasoning step where they're fine-tuning the model and they're able to do this sort of reasoning trace operation. And so, while typically no optimization pressure is applied to the intermediate tokens, empirically it's been observed that language models perform better on many domains if they output such tokens first. While the fact of the performance increase is well known, the reasons for it are less clear. Previous work is often framed in anthropomorphic terms, claiming that these models are thinking before outputting their answers. Simultaneously, the process of performing more autoregressive forward passes before outputting the final answer has been credited as an instance of interference time scaling. That is, these models are assumed to be doing the problem adaptive computations that we it's assumed to be doing problem adaptive computation. Famously, DeepSeek's R1 paper claimed that one of the most impressive observed behaviors of their trained models was the so-called aha moment. I think we talked about this before as maybe like the oh shit moment. And like this is actually something that's in the I know in the cognitive neuroscience literature where there's this aha moment. So this is where in humans you'll work on a problem and you'll be exposed to things and you acquire knowledge, and then there's this aha moment where you get an insight. And so this is something people have studied in human cognition. And this is so they're kind of making this analogy to human cognitive neuroscience, human cognitive neuroscience, where they've identified this aha moment, both in terms of behavior and in terms of the neuroimaging. As part of the chain of thought that it was producing in order to answer some question, the model output token aha, seeming to indicate that it had come upon a sudden realization. While a human may say aha to indicate exactly a sudden internal state change, this interpretation is unwarranted for models which do not have any such internal state, and which on the next forward pass only differ from the pre-aha pass by the inclusion of that single token in their context. Interpreting this token as meaningful in this way requires making an additional assumption that has thus far been brushed to the side in discussions of how long chain of thought models function, what they do, that the derivational traces they produce are semantically meaningful in the same way that traces that they were trained on, or at least in the way a human might expect them to be. So this is impossible to check for a lot of large models. The intermediate tokens of massive pre-trained and post-reinforcement learning models produce meander for dozens of pages and are written wholly in ambiguous and polysemantic natural language, and, perhaps much worse, are the result of long, opaque training processes on data that we have no access to and cannot compare against. So this is, again, for R1, you have this reinforcement learning step at the end. So a lot of this sort of last step, this reasoning training is done through reinforcement learning, and it's, if it's not, this is where you get this ability to sort of trace things and reinforce reasoning. So they have another point up here, which is interesting, which is that we're oftentimes inferring an internal state to these to large language models. And so this is something that we do in human cognition all the time. We talk about internal states, and the internal states aren't necessarily related to a certain circuit. It's sort of, maybe it can be related to a circuit, but it's this sort of assumption that there is this internal state that's being generated, that there's this behavior, there's this activity, and then there's some internal model or internal state that's being regulated, and then there's, it's basically the output. So you see this a lot of times in emotion, where you have emotional states or you have cognitive states, and we have to sort of have a placeholder, an assumption of this internal state. So that's kind of, and then of course, in large language models, we have a similar thing where there's some sort of internal state. It's sort of the collective behavior of the circuit and its activation. So this is another thing that, we do know better in studying human cognition, but it is something to think about as sort of this thing that we're making an assumption about. Okay, I think that's all for that paper. So we had, these are all things that are in the Slack. Thank you for the people who've posted these in the Slack. I think it's like Morgan and Vidhi for posting these things. All right, so why don't we come back to this discussion? I'll do one more thing. So I wanted to talk a little bit about this. Brain-inspired meeting that happened this week. So last week we talked about the fact that there was going to be a brain-inspired reading group meet on this Rosenbluth et al. Paper, the one that Jesse wrote the blog post on, and it was very good, very in-depth. And so the discussion group hadn't happened yet, and so I wasn't able to make the discussion group, but Jesse was, and I think Morgan as well. So this is Jesse's post on this. And so this is Paul Middlebrook's Brain-Inspired Complexity Group hosting Malcolm Lett, Andrew Pickering, Luis Pizoa, Sean Manny, and Anna Rydell, Kevin Mitchell, Darren Locke, Morgan Hough, and many others. Discussing the 1943 paper Behavior, Purpose, and Teleology. And this is the paper that in question is part of David Krakauer's Santa Fe Institute Foundational Complexity Paper Series. What an interesting discussion about the history of cybernetics and how many of its associated adjacent fields developed. Developmental biology, systems engineering, cognitive science, AI, teleology versus behaviorism in various historical contexts. The paper was a response to the prevailing scholarly attitudes that dismiss teleological explanations as unscientific and obsolete. By redefining purpose in terms of feedback, Rosenbluth, Wiener, and Bigelow sought to rehabilitate the concept of teleology, striving towards a rigorous framework that would account for goal-directed behavior in both biological organisms and in machines. And so, yeah, he points to his discussion of the paper. And so I guess I don't have the original post, so this is going to be kind of hard to read. But this is kind of a screenshot here at the bottom. They talk, I guess, about the source material for cybernetics. There's this juxtaposition of proto-cybernetics and complexity. And then this is a screenshot of people discussing the paper. So I guess I had some discussions with Jesse in the Slack about this. And so this is his message in the RG side channel. This is a cybernetics reading group channel. And this is the link. This article, I think it's from MIT Press, from Newspeak to Cyberspeak. He says, also happening now, brain-inspired complexity discussion on the 1943 paper. It's mostly about cybernetics right now, and almost nothing about the paper so far, to be honest. And I responded with a laugh cry, because it's kind of funny that sometimes you have these discussions about papers that go sideways. Like, I don't mean sideways in a bad way. I just mean like they don't, it's like people will talk about like the history of cybernetics and get stuck there. And, it's just kind of funny how that went. And so then I said, and then we talked about I saw that post and this term proto-cybernetics. And I had to ask, how are they defining proto-cybernetics? Do you mean proto-complexity? So, we talked about complexity theory and how it sort of formed out of these concerns about reductionism and some of the methods that we used to study interactions between things and emergence and things like that. And those kind of came together in complexity theory. And of course, David Krakauer's book, the one that Jesse referenced, has been referencing in our lab. That's a very good introduction to sort of the antecedents of complexity theory, because it goes through these papers, the 1943 paper being one of them, that kind of contributed to modern complexity theory, at least the Santa Fe flavor of it. So I thought, maybe they were also going to talk about proto-complexity, and I was curious as to what they meant by proto-cybernetics. There is this sort of history of analogies like the Steersman analogy and the name cybernetics being sort of a Greek root word. So there's been this, it kind of draws from the history of thought, the history of natural philosophy. And so I was just curious what they meant by proto-cybernetics. And so Jesse says, just in the sense that the paper was before cybernetics was coined. And yeah, cybernetics, of course, we know that there were these Macy conferences in the maybe late 40s, early 50s, and this came a little bit before that. But it's interesting. I don't know if people have kind of formally defined that as proto-cybernetics, because there is a lot of stuff that, say, Norbert Wiener was doing before cybernetics, or some of these other people were doing before cybernetics was coined or became a hot topic. So yeah, it's interesting, and it might be worth having a separate kind of discussion or set of discussions on what kind of came before cybernetics or what kind of led into cybernetics. And then Jesse said, maybe I will change it to that word. The discussion itself is basically 60% plus about history and takes in politics around cybernetics, which was actually interesting to me, but I don't think it related to the complexity discussion much. And then I said, actually, some discussion on where cybernetics came from is quite interesting. A lot of cybernetics is born of describing a new world of the time, which involved communication and computer technology. So if you think about information theory, a lot of that came out of Claude Shannon's work on telegraph technology, telephony, things like that, which were a newish technology, and you had to sort of optimize communication channels for those devices. And then from that, we got this theory of information, which has been applied in many different contexts. So, you have these things that are born out of sort of an immediate need of the time, and then they became this sort of almost with this universal or universalist sort of assumption that those kinds of models, as kind of theoretical models, apply to the world at large. So, again, that's an interesting thing to kind of think about and explore. And then, of course, there were these older concepts that had to be merged with these newer technological realities. So as you had communication and computer technology and, systems that required us to think differently, not just in a purely reductionist way about function and things like that, we had to come up with a new theory, but we also had tools that were available to us that came from the past. And so we can think of this as like ancient Greece, the insights of ancient Greece. We also had to reconcile some of the religious thinking about things like teleology with sort of a modern conception of things that, maybe look teleological or actually are teleological, and kind of reconcile that. And then think people like Claude Bernard, who proposed homeostasis, which was developed, in later by Walter Cannon and other people, where, in Bernard's conception, there was this milieu, French word meaning this kind of world where things were regulated. And Bernard, didn't offer a lot of technical rigor to that. That came later. So you had these concepts like homeostasis that were kind of, maybe early scientific, and then they had to be updated. So I just thought that was really interesting, that whole set of things that come together, not only to inform cybernetics, but complexity as well. And then I asked, what are the politics of cybernetics, by the way? So then finally, Jesse responds to that question with this. There was a lot of discussion about basically Cold War impacts on its real-life implementations for governance and other things. And of course, we know that, we had a lot of cybernetics work went into military applications. We know that a lot of the work that was done at the University of Illinois, there was this lab, the biological computing lab, that was funded basically by military funding. And when that ended up getting pulled or no longer being available, the lab kind of went away. And so there was a lot, oftentimes that's the case in engineering, where you're funded by something like a military grant or some sort of grant, and then you can have the freedom to explore other things. But there's always that kind of, people kind of see the practical application as the military grant or the corporate grant. And it's really kind of a, it's kind of a weird kind of dual existence for things. And then, of course, Project CyberSyn, which was, also had political undertones. Project CyberSyn was mentioned lightly, but also other things regarding Russian cybernetics. And we talked about Chinese cybernetics in our cybernetics group at one point. So there were different schools of cybernetics around the world. It wasn't just in the US and England. There were, I think Chinese cybernetics, we talked about some of the things they were doing kind of in parallel to the people in the English-speaking world, which actually is true of a lot of the history of science. There's like German embryology and Russian embryology, and all these like fields of embryology, subfields of embryology that were very prominent, like back in the 19th and early 20th century, when people didn't translate articles as much. There wasn't the standard of English in the international scientific community. And so you had these whole communities where everyone would communicate, say, in Chinese, they would be in China, and they would do their own kind of work. And I'm sure that's true to an extent today in different places in the world. but it's not like it used to be where you would just be isolated from other countries. So like the German embryologists, for example, were notoriously sort of resistant or late to the party in terms of reading the works of Charles Darwin. So it's really interesting to look at like late 19th century embryology, German embryology in that respect. So also interesting-ish talk about teleology and quote unquote God stuff. And yeah, I'm not sure everyone understood just how much the paper was intentionally reclaiming teleology as a term, or like why it mattered or needed to be reclaimed. It would be interesting to review that discussion and compare it with some reading group cybernetics, reading group videos of the past, which we have on our YouTube channel. This is we have a playlist for the cybernetics reading group, and we've done a lot of interesting stuff in that reading group. Gone through a number of books and papers, and so that's something that we should revisit if we're interested in these sorts of things.
It was interesting. I think the videos are recorded, but I think it's fair to say at least half of it, and I think Morgan was there. At least half of it was really like just background and not really about the paper and kind of what is cybernetics. It was on a personal note, and I think Bradley, you'll know this more than most other people. It was basically the discussion was probably about 60 to 70% of what I really was looking for when I started a long time ago on my original sort of project, way before I ever joined the lab, of what happened to cybernetics.
Okay.
Like they were all answering the questions of these political forces, and then a lot of like Cold War and esoteric stuff, like not just the 30s and 40s and 50s, but kind of 60s and 70s, which I didn't have a lot to talk. I'm probably least familiar with that because I don't know. I guess I would slant towards earlier stuff.
Who was the guy who joined, who had all this like personal history stories?
Andrew Pickering, the old guy, or the
okay.
Yeah. Andrew Pickering, I think, was sort of the guest person, and he's obviously written was it the Cybernetic Brain book? I forget.
Yeah, I think that's it.
Yeah, and it was cool because it was sort of nice to actually have a multi-generational community. Like you had the, I don't know, high school undergraduate kids who showed up, asked a couple questions. You had Andrew at the other end of the spectrum, and it was sort of like big intellectual family learning and sharing time, which was it was quite wholesome in a way, which is ironic because a lot of the topic was like, what was the weird stuff going on during the Cold War and how are cybernetic used? But it was more than that too. We did get into the paper, but some of it was, I don't know. It was so interesting because I feel like what we covered and how we came to the paper in our reading group was actually almost one of the lesser represented views on it. And I guess view maybe isn't really the correct word, but more our history and the deep dives that we took. Like everything you said in the Slack, I think would have been interesting and relevant. Not that people didn't know it, but more it didn't. I don't think it. If I had more time to prepare, and I did mention this, I did say this in the meeting briefly, but I would have loved to kind of more thoroughly emphasize and explored directly, or at least offered some don't want to say competing, but like maybe, wow, I sound like I sound a bit like a late night infomercial when I'm saying this, but not competing, but completing, but really sort of a completing narrative to it, because I think there was a little. It kind of took a while for everybody to collectively wrap their heads around. Well, why are we talking about teleology? Like what was the tabooness of it, and is it taboo at the time? And in the paper in the background, like it, yes, like it was a big deal to weave into this, structure of, well, maybe even a better way to say it is to extract from the structure of sorry, I'm just adjusting my situation here. The repurposing of it, like it was a very intentional argument against, well, as an intentional move to quote unquote reclaim teleology, or at least try to distance from it so that it could be used to do this thing that would become predictive and create these lenses of analysis based off of feedback at the time. Like there were some questions about, well, why is it negative feedback? And I kind of wanted to, I wish I had more ability to interject and kind of get into, well, it's negative in the construct of what they're saying, because negative feedback is related to distance from a goal. Like and that's how they're spinning purpose and teleology. And they're doing all of this to get away from the perceived woo-woo taboo God stuff, and empiricism, and the, I'm not even saying right or wrong about it. I'm not really even trying to be reductionist or anti-reductionist or polemic about it, but just there was a very specific juxtaposition, which I think maybe to us from now in 25 is almost relevant. Excuse me, is almost irrelevant seeming, or like, well, everybody feels that way now. But I think there was an important context that could have been emphasized just a little bit more. That were things that we centered a lot in our previous discussions. So there's more to say than that. But I'll kind of say that, and then hear if you want to say more. Morgan wants to say more, and carry on.
Well, I just wanted to get your ideas about it. And yeah, Morgan, let's move on to you. And I know you wanted to talk about the large language models as well. So what are your thoughts about all this?
Sorry, I'm multitasking here.
Okay.
And so in terms of the complexity discussion?
Yeah, I can start there.
Yeah, I mean, at some point, Paul did say, like, so does anybody want to talk about the paper?
Yeah.
Right. Yeah. And I was waiting for that too, but I was like, that's why the tension for me was like, I kind of want to talk about the paper, but also like, I as I just said, like, I've had this, like, one of my original reasons to even come down the path that I'm down was literally what happened in cybernetics. So it's like, I don't want to interrupt this like vast context that was circumstantial, and not all of it, but it was mostly like discussion 20, 30, 40 years after the paper was written. for the first half hour or so.
Yeah.
Like, okay, well, I did want to know this, but we did get to the paper.
So I mean, that was funny-ish. That said he had to say that. but I'd certainly, I could understand why the discussion went the way it did. Anyway, the language models work. I'd like to get into, but would like to be in front of a computer where I can see what I'm talking about. So
Okay,
I will need a bit more time.
that's okay. Yeah.
But very interested. I can throw in just a few things that happened this week.
Okay.
That were certainly interesting too. The Foresight had its NeuroSim here this week, and we had the founder of Eon Systems talk, and I was pleasantly surprised to see that it involved more than just advanced connectomics. They're definitely trying to capture living systems over time. Again with certain caveats and certainly not doing developmental neurobiology. And I thought it was funny that he was talking about all these amazing things we could do, but somehow like understanding the brain wasn't one of them. It was just like, oh, we're going to be able to do this, we're going to do that. And then somebody was just like, oh, well, so, does this have any kind of regenerative medicine applications, or does this have any, and he's like, oh, we don't, this doesn't understand, how the brain works. It's just like, well, wait a second. How are you getting anything if you're not capturing brain activity, or starting to form some sort of model of what the brain is doing? Anyway.
Yeah. So that basically the idea there was they want to collect data, but they don't want to say anything about anything else.
Well, they want to collect data for this for this whole brain emulation, right? But it's where you suddenly jumps to a conversation that's reminiscent of altered carbon, and but somehow but we're not solving any brain challenges here. Like we're not doing brain science,
right?
And I kind of feel like, well, you should be.
Yeah. It leads to that conclusion, right? Yeah.
And there was this totally it doesn't totally relate, but I think it does. I mean, it was an article. Oh crap! Please tell me I saved it. It was an article about the complexity of biology, and kind of like asking the question: do the tech people really think that they're just going to come in and disrupt biology?
Yeah.
When let me just see. Yes. Okay. Yes. And this, can tech founders really disrupt biology even when the top scientists only understand tiny pieces of it? At places like Stanford, EMBL, Harvard, entire departments of brilliant scientists. Well, yeah, okay. It's not their brilliance; it's just the complexity of it, right? So, and then they've got a picture of the most comprehensive computational model of human metabolism, which is this massive of massive wiring diagram, right? And I kind of feel like that kind of describes whole brain emulation. Where
Yeah.
it's just like, it's this tech story that tech people have sold themselves. um, and I'm still waiting for I mean, I just think it's super important again to say, like, AlphaFold, as amazing as it was, right, did not, well, it's still going to be a long time, and a lot more AlphaFolds will need to happen before you even get into cell function.
Right.
Right? like you're not at cell function at AlphaFold, right? You're still at confirmation, right?
Yeah.
And yeah, anyway, so I just think somebody doing brain emulation should say a bit more, should say that they will necessarily be solving brain challenges on the way. But I don't know if that's, again, just yeah. At the same time, I'm jealous. These are people who are raising money,
Right.
so maybe they're onto something.
Yeah. Yeah, this goes back to, like, I think recently in our meetings we've talked about the main criticisms of the Human Genome Project. 25 years later, the idea being that we produced a draft of the human genome. We have a good understanding of the sequence, sequences in the genome, but we don't know exactly what the functions are. We do have some knowledge of the functions. We have annotations. We have some experiments we can attach to certain genes, and we have genome studies where you can look at how much different genes contribute to different traits, and those are like GWAS and things like that. But other than that, it's like, what is the Human Genome Project still hasn't really given us a lot of functional insights. And so, that's something that, of course, when they understood that, I think, when they did the Human Genome Project, that it was just a beginning step of kind of giving you the tools to get to those insights. But and so in that sense, that wasn't the original intent of the project. On the other hand, there is this expectation by people that there's, like, it naturally lends itself to insights. And maybe this is an expectation setting problem. Maybe this is a problem more generally of the hardness of the problem of, like, actually finding biological function or identifying it and knowing, getting familiar with it, as opposed to, like, sequence data, which is easier, I guess. And so, that's maybe where we are with the brain as well, where we have, it's very hard to get to this step of understanding. It's easy to build, like, circuit diagrams or, finding sort of these identifiers, as we might call them, but it's harder to get the insight into behaviors and things like that.
Yeah, absolutely. I mean, you remember how upset I was with the schizophrenia research guy talking about the failures of the Human Genome Project. And I felt like the failures of his science education.
Yeah.
But yeah, and well, I'm super, I'm interested to know more about what he's trying to capture with time. I mean, in terms of like he does actually want to image live samples. so some of the larger, more well-funded projects are definitely just advanced connectomics with, using expansion microscopy and things like that. It was an interesting discussion of expansion microscopy. So somebody asking if it was destructive, and everybody's funny response where they're like, the most is destructive.
The most destructive method possible, really. Well, maybe not, but yeah.
Yes, like slightly less than just blowing the sample up.
Yeah.
And then so there was an interesting discussion of kind of the necessary reconstruction that is involved in expansion microscopy.
Yeah. Yeah. So for those who don't know, expansion microscopy is where they expand the tissue, blow it up, basically, like swell the tissue so that they can see they can get greater resolution, and then they do the microscopy. So if you have a very small feature, you expand it out, and then you get to see it. And I guess you correct like the shape and all that, just right.
Yeah, you really gotta kind of piece. It's a little like forensics.
Yeah.
As you kind of piece things back together,
right.
But at the same time, it's what you've lost with the destructiveness you've gained with the kind of interior visibility.
Right. I don't know if you had more, like if you want to do more insights on the large language models later.
Which paper did you cover?
For what?
For the large language model discussion?
It was, we had the paper on, so we talked about this paper, Beyond Semantics, the Unreasonable Effectiveness of Reasonless Intermediate Tokens. I think this was posted in one of the Slack channels. And it has that title again, the Unreasonable Effectiveness of Mathematics Play on Words.
Right.
Like, and so the idea is that there's this, like, I guess the intermediate tokens are maybe not, cognitive in the sense that maybe we ascribe the function that we ascribe to it. And so, yeah. And then we talked about some of the circuit tools. We talked about Neuronpedia, which is a tool from, I think, Anthropic, and then this other tool, Transluce, which is another model from a research group.
The work that they've done is impressive in terms of trying to bring out explainability. Right. But I haven't done the work to.
Oh, that's okay. Yeah.
To really do it justice. There was some interesting, what's the paper? I forget. I think I put it in Dev Neuro AI. Russ Poldrack had recommended the Stanford, computational psychiatry LLM paper as very much showing you should not be using this as your therapist. The funny comments to this was like, did this really need to be a paper?
Yeah. Yeah, it seems kind of obvious.
Yeah. I mean, that was probably the most common comment. Which is funny.
So why don't we pull up the Tokens to Thoughts paper that Morgan discussed. So this is on the archive. It's from Tokens to Thoughts, How Large Language Models and Humans Trade Compression for Meaning. And so the abstract reads, humans organize knowledge into compact categories through semantic compression by mapping diverse instances to abstract representations while preserving meaning. So, for example, robin and blue jay are both birds, therefore most birds can fly. Or, you can make that inference. You can take birds, you can take instances of birds, you can attribute functions to birds, and that, of course, not all birds can fly, but you can generalize from the concept of birds. You build upon your concept, and then you generalize to some behaviors, and you have this model of birds. You also have this model of robin and blue jay, and you can basically you're mapping these different instances of something to this representation, and you're preserving the meaning of the instance, but also providing this context and this larger category. So that's how we're basically, or humans use language to construct these mental models or these internal models. These concepts reflect a trade-off between expressive fidelity and representational simplicity. So expressive fidelity is where you have this, ability to, have sort of a good representation that represents all the different instant categories for which something is true, but also in cases where it's false. But also representational simplicity, meaning that you don't want to specify every single thing and every single exception to this representation. So you want a simple type of representation, maybe a low dimensional representation, but you also want to have something that's accurate when expressed in different ways. Large language models demonstrate remarkable linguistic abilities, yet whether their internal representations strike a human-like trade-off between compression and semantic fidelity is unclear. So we don't know. Well, we think that this is what's happening in humans, but in large language models, we're not quite sure whether these internal representations have this same kind of trade-off, or this optimized trade-off between these two things. We introduce a novel information theoretic framework, drawing from rate distortion theory and the information bottleneck principle, to quantitatively compare these strategies. Analyzing token embeddings from a diverse suite of large language models against seminal human categorization benchmarks, we uncover key divergences. While large language models form broad conceptual categories that align with human judgment, they struggle to capture the fine-grained semantic distinctions crucial for human understanding. So again, these where large language models excel is in forming these broad conceptual categories. And these largely align with how humans form broad conceptual categories. But then, of course, they struggle to make these semantic distinctions. So you'll get these categories that look like they're, sort of human cognition, but then they can make a lot of errors that are not typical of human cognition. So that's, kind of just drawing out the distinction between large language models and human cognition in terms of representations and in terms of this expressive fidelity. And, expressive is a term that they use in computer science, not so much in cognitive science. So it's worth noting that this is not something that we necessarily have an analog for in human cognition. More fundamentally, large language models demonstrate a strong bias towards aggressive statistical compression, whereas human conceptual systems appear to prioritize adaptive nuance and contextual richness, even if this results in lower compression efficiency by our measures. So this is where, in large language models, it's all about compression, statistical compression, and how to, encode those things in that way. And then in human conceptual systems, there is this emphasis on nuance and richness, despite, the need for, I guess there's less of a need for statistical compression. And in fact, human conceptual systems work against this in a number of ways. So it's more important in human systems to have, or at least human systems have this ability to find nuance, to deal with ambiguity in different ways, and to go from context to context. And this is exactly the thing that large language models struggle with, and some of that has to do with this sort of statistical compression regime under which these models operate. So, is this a product of sort of the technical limitations of large language models, where you need to have, despite the large amounts of computational power that they already require, you still need to compress statistically the representations? Or is it, this is something that human conceptual systems are adapted for, and so really do emphasize. So, the argument that large language models are basically the same as human cognition is, in this case, at least false. And there's a very fundamental distinction here. Human conceptual systems have this lower compressional efficiency, and so that's, maybe that's a good thing. But if you're looking for compressional efficiency, it's a bad thing, I guess. These findings eliminate critical differences between current AI and human cognitive architectures, guiding pathways towards large language models with more human-aligned conceptual representations. So this is, maybe something that we can use to illustrate how to make large language models more like human cognition. To say, okay, this is what we need to focus on. But yeah, and so I don't know. Let's look at the paper itself. So they kind of go through, and they highlight this framework for comparing compression and meaning. So to understand how large language models and human cognition grapple with the fundamental challenge of representing meaning, we introduce an information theoretic framework. This framework is designed to analyze the critical trade-off or tension between compressing information into efficient representations and preserving this rich semantic fidelity essential for true understanding. So this is the point that we made in the abstract, drawing upon core principles from rate distortion theory, which is something Claude Shannon introduced in 1948, and the information bottleneck principle, which was introduced by Tishby in 2000. Our approach provides a cohesive lens for addressing all three of our research questions. So their research questions are as follows. The first one is probing representational compactness via categorical alignment. And so they want to know how information is condensed into categorical structures. How do you take information and put it into a categorical structure? Is this, it isn't just simply a matter of throwing things into bins. There's this whole process by which we take information and put it into categorical structures so that they have some comparable amount of information. Both human categorization and large language model derived clustering simplify diverse items X into structured groups C. So we have all these different types of things that we want to put into categories. We want to structure the groups so that you don't have, things that are categories that are sort of not useful. But you want them to be broad enough so that they represent the true sort of diversity that you see in the world. So they assess alignment between model-based clusters and human categories. So it's CLLM and C-human. By quantifying shared information. So this is based on mutual information, which is where you take two things and you look at the overlap in the amount of information that they share. And so you can use information theory to get this number, offering an initial view on how similarity compactness is achieved. This principle this principle of efficient input representation here relates to the complexity aspect of our framework. The second question is probing semantic preservation with internal structure. So they want to assess how well meaning is preserved within these compressed representations. So we have compressed representations for large language models in humans, and then we want to know how well semantics are preserved within each type of model. For research question 2, we investigate this by correlating large language model internal measures of item centrality with human typicality judgments. So we're using two different sort of criterion, but we're trying to sort of compare. So in large language models, we use item centrality, which is a measure of sort of these clusters. And then in humans, you use these typicality judgments. So you're basically trying to find the mean thing in that category, the mean object in that category. And whether that helps you with these out of distribution things is, I don't really know the answer to, because out of distribution objects are by definition either things that are atypical or things that have not been seen before. So it's hard to sort of calibrate that to these kind of mean categorical exemplars. In any case, you have these two different kind of criterion or ways for viewing this. And so then we want to probe how faithfully fine-grained semantic information is represented. So for example, can large language models capture the internal structure of C humans? So can large language models capture what happens in human categories? Or given that human categories are fundamentally different, at least in terms of how they're sort of formed, can large language models capture that directly? And so this relates to the distortion or the fidelity aspect of our framework. And then research question 3 is evaluating the integrated trade-off of total representational efficiency. So having explored compactness and preservation in the past 2 research questions, we leverage our full framework. Research question 3 employs a unified objective function, which is detailed below, to quantitatively assess the total efficiency with which large language models and human systems navigate this fundamental trade-off. So that's how they're approaching that problem. Very information theoretic driven. Okay, so any questions on that?
And that just, as deep parallels in how people study language and humans.
Yeah. Yeah, it's a hard thing because it's like you can't just make the assumption that they acquire information in the same way or they do categorization the same way.
Yeah, no, for sure. And again, I mean, it gets back to this. I'm not one saying that we should use them as synthetic humans, but we should certainly approach it in the same way that we do experimental psych in general.
Yeah.
And you gotta figure out the space, and it's measure.
So let's move on to our final thing for today. This is, we've been talking about cybernetics and how, sort of the antecedents of cybernetics and how there's this legacy of cybernetics, especially for artificial intelligence and some other areas of science. Norbert Wiener, of course, was a main figure in cybernetics, and he had, of course, we've talked about his arc of intellectual production, and it's really fascinating. He's not just a cybernetics person. He did a lot of work on information theory and some other areas of science and engineering as well. This is a Medium article. This is by a CEO of AI Soma AG. I'm not familiar with that, but it was an interesting little article. Norbert Wiener's Understated Legacy in the Age of AI. So this is, of course, generated by DALL-E. It's a picture of an old Norbert Wiener, I guess, with chalkboards and so forth. So the article talks about sort of Norbert Wiener's influence on AI research, which is not necessarily apparent to people from kind of at first glance. He did, of course, the book, The Human Use of Human Machines, which we went through chapter by chapter in our cybernetics reading group. He also did a lot of things on information theory, did a lot of things on cybernetics and feedback. And so all those things are kind of setting up sort of modern AI research, but also sort of modern cognitive science, because modern cognitive science uses this sort of cybernetics view of things. And so this is, definitely a worldview that Wiener sort of was at the formative cusp of, and so this is something that we would like to know more about. So Norbert Wiener's work has a lasting influence on AI research, but unfortunately is less well known to the general public. Norbert Wiener was a mathematician and philosopher who made several significant contributions to the development of artificial intelligence. Wiener's most crucial contribution to artificial intelligence was the development of cybernetics, which created some of the theoretical foundations for modern artificial intelligence. Cybernetics dealt with the control and communication of machines and living organisms, and was an interdisciplinary field that drew on insights from mathematics, engineering, biology, and psychology. So, we talked about the cognitive science hexagon, which has it's a shape that has at each point, at each sort of vertex, a field of study. So, cognitive science, I don't remember all the 6 fields that contribute to cognitive science. It's like philosophy, mathematics, psychology, anthropology, computer science, and one more, or linguistics, I guess. And so, cybernetics has the same structure, where these different input domains, these different input fields, and they contribute to the interdisciplinary field. So it's, I don't know if you want to overlap cybernetics with cognitive science, so the cybernetics cube or square with the cognitive science hexagon, you're welcome to do that. It would be interesting to compare. As Wiener astutely observed, we have changed the world more than we have changed our way of thinking, and the new way of thinking is still partly that of the preceding stage. This is actually an important point for what we were talking about with respect to the reading group, the history of cybernetics, and that is, the purpose of that 1943 paper was to sort of change the way of thinking. So it's not enough to just kind of introduce ideas into the bloodstream of the intellectual world or into a field. You have to kind of change the way of thinking. You have to propose maybe how terms should be redefined, or how, like this last paper we talked about, to remind people that we're, what the fundamental challenge actually is, because sometimes people lose sight of this. Sometimes a lot of ideas get interpreted, and there are a lot of sort of atavistic ideas about, say, communication and control that persist. And so, sometimes you need to write a paper to remind people that this is a fundamentally new thing we're dealing with here. I'm talking about in 1943, not in today's thinking, but so we need to really kind of reframe everything. We need to reframe everything we've been thinking about before. We can't just take our old ideas and move them into the future. We can't just take human analogs of thinking or change over time and just kind of work with those. We need to kind of fundamentally rethink those. So in this quote, Wiener predicted the trajectory of technology and the human propensity to underappreciate the frameworks that fundamentally reshape our existence. Wiener's work on cybernetics was based on the idea that machines and living organisms can be viewed as information processing systems that rely on feedback and control mechanisms to remain stable and adapt to changing conditions. So this is like where we talk about homeostasis and allostasis and things like that, much more than just that simple feedback and control mechanism. Norbert Wiener's work on cybernetics and feedback laid some theoretical foundations for artificial intelligence. His insights into the similarities between biological and mechanical systems have significantly influenced its development, and his concepts of feedback and control remain fundamental in the development of modern intelligent machines. I think Wiener would like this quote: "Artificial intelligence is highly interdisciplinary. Therefore, let's approach it as a multidisciplinary and holistic discipline." And so I'm paraphrasing that, but it's still interesting. And then there's this book, Cybernetics, second edition, where the control and communication in the animal and machine. So that's that article. So it's interesting, kind of a motivation for this paper, which I found. This is a paper from Steven Strogatz, and this is Norbert Wiener's Brainwaves. I thought that would be a nice way to finish up the meeting. Kind of stitching together some of Wiener's work that's maybe inside of cybernetics and some that's outside of cybernetics, since Wiener did a lot of work on signal processing as well. And so this is basically discussing his work in this area. So this is the introduction. Let's see if I can zoom in here. Okay. In the late 1950s, Norbert Wiener became interested in the spectrum of human brainwaves. So he published some papers in the late 50s and early 60s. Along with his medical collaborators, he made high-resolution encephalographic recordings from subjects who were awake but resting with their eyes closed. Under these conditions, the electroencephalogram showed conspicuous activity at frequencies around 10 Hz, or the so-called alpha rhythm. Figure 1, which I'll show you in a minute, shows Wiener's sketch of the magnified spectrum around 10 Hz. He writes, "It would have been quite conceivable that there would not be a phenomenon of that sort. For example, it might have been that all of our work on the fine structure of the brainwaves is wasted. However, once we find this effect, we are under an obligation to try and give an explanation of it. There are two things that are striking here. One is the very narrow line at the center of the spectrum, and the other is that this line arises from a dip. So let's look at this figure 1. So this actually looks like a wavelet. I think the Mexican hat wavelet specifically, but this is basically what he's discovering in human alpha waves. So this is the frequency, this is the 10 Hz band here, there's a maximum here, and then it falls off around 10 Hz. And then there's this dip on either side of 10 Hz, and then there's this increase in going sort of up in frequency and down in frequency. There's these secondary peaks, and then there's this fall off after that. So these are human alpha waves. This is what they discover in their work. This is the schematic sketch. So it's basically the idealized wave, but this is basically what they're looking at. And again, it's, it's interesting because, why does it do this? You would think, well, okay, there's some peak at a certain frequency and then it falls off and that's it. But this is something that, is not a normal distribution. And, maybe you shouldn't expect to find those in time series or, in the frequency band, but that's what we have. So to explain the spectrum, Wiener hypothesized that there is a population of oscillators in the brain whose intrinsic frequencies are close to 10 Hz, and that these oscillators constitute a more accurate oscillator and mass than they do singly. So that means that you have in this frequency portrait, you have a bunch of things underlying the signal. So you're recording a signal from a site, you have this 10 hertz band, and because there are a lot of things contributing to it, you have this complex function. And so it's actually, these oscillators are kind of operating at this frequency close to 10 hertz, and if you average it out, you get to 10 hertz. And it's a nice, neat marker, and it has like a lot of significance in the brain, I guess. But the point is that it's not produced by a single signal. It's actually the product of a number of oscillators, kind of operating maybe stochastically, but kind of collectively giving you this 10 hertz signal. The idea is that the oscillators interact by pulling on each other's frequencies. So they're interacting as well as producing independent signals. So if an oscillator is ahead of the group tends to slow it down. So Stephen Sturgatz has been interested in synchronization his entire career. He wrote this book, Sync, about 20 years ago, where he was talking about a lot of the stuff that people do when they study firefly synchronization. So fireflies will synchronize their flashing activity, and they'll do it by communicating with each other and using the signal as their luciferase signal as a way to synchronize each other's flashes. So this is something that we also see in like the Kuramoto oscillator, which is a model of different neurons oscillating in a population. And each neuron is influencing other neurons in that population. So basically, the oscillators are behaving in a way that's regulating the entire average. And so what you see in this trace is where this is kind of, this is an active process. It's not something that happens automatically. It happens kind of dynamically, and sometimes you never get to the actual average. But you can see that the average behavior of the oscillators is at 10 hertz, and then there's some variation around the edge. And so these dips represent places where, you have less activity. And it's just because they're operating around this mean, and there's this space where, as they're correcting each other, where they are less likely to inhabit. So you're basically describing sort of this complex system in this simple trace. If it's going too slowly, the group tends to speed it up. In this way, the population of oscillators can achieve a collective enhancement of precision. This is basically also the way that collective movement of bird flocks are described. If you go back to some of the models of collective behavior in bird flocks, basically the way people formalize this is that birds exist in this flock, that individual birds will kind of behave, and then they'll monitor the behavior of their nearest neighbors. And so the way that bird flocks are sort of coherent and stable is that they just basically slow down when the neighbors slow down and speed up when their neighbors speed up. And so they correct themselves to the average or the mean of the group. And so this just propagates across these, individual birds communicating with their nearest neighbors, and propagates throughout the flock until you get this coordination of the flock. And of course, you'll see this mean behavior, but you also see these weird transitional states, which actually allow the flock to recover to another stable state. So this portrait here that we see, you could extrapolate this out to other types of synchronized behaviors as well. Wiener tried to support his notion of frequency pulling with the experimental evidence available in those days. For instance, he mentions an amazing experiment involving direct electrical driving of the brain. A sheet of tin was suspended from the ceiling and connected to one terminal of a 400-volt 10 hertz generator. He writes that this apparatus can produce electrostatic induction in anything in the room, and that it can actually drive the brain causing a decidedly unpleasant sensation. I bet it would. So this is an experimental kind of setup that he made for this. It is probably wise to take Wiener's experimental claims with a grain of salt. He rarely shows or cites actual data. Figure 11 in Wiener in 1961 is the lone exception, and as far as I know, no one has ever replicated his results. Wiener 1958 also attempted to account for his observations mathematically, but his approach was awkward and led nowhere. However, he did leave an important legacy. He was the first to propose studying the collective behavior of biological oscillators. So this, again, was sort of the basis for some of the synchronization work that came later. So Wiener's work was 1958, 1961, and then this led to people like Art Winfrey, who published in 1967, 1980, 1987. He did a lot of things with, wrote this book, The Geometry of Biological Time. Also did a lot of work with oscillators. These oscillators range from chemical oscillators to neuronal oscillators to other types of collective behavior. So examples include pacemaker cells in the heart, lycotic synchrony in yeast cell suspensions, collective oscillations in pancreatic beta cells, synchronously flashing fireflies, crickets that chirp in unison, and women's menstrual cycles become mutually synchronized. So these are all examples of this sort of type of mutual synchronization work. So where Wiener kind of couldn't land the fish, these other groups had worked on very specific systems and actually have made quite a bit of progress in this topic. And again, there's this assumption of universality where you have all these different types of systems and they are all driven by this, I guess, I wouldn't want to call it a simple mathematical law, but the simple principle of organization. We review some of these examples in section 2, and then in section 3 in this paper, we consider the classic model of mutual synchronization. The analysis of this model over the past 25 years has drawn out a wonderful range of subjects, of course nonlinear dynamics, but also statistical mechanics and even plasma physics. And as we'll see, Herbert Wiener's spectrum has almost been explained in a mathematical sense, but not quite. So this spectrum in figure 1 that I showed you, that was something that people have tried to figure out and explain in a mathematical sense. They give some biological examples, ranging from pacemakers to Kerr model oscillators, and we won't go through that. But these are some of the afterthoughts and kind of thinking about how maybe some of the mathematical explanations for this. The intuitive leaps in Kuramoto's analysis deserve our admiration, but they have also provoked some vigorous head scratching. And this is, of course, the Kuramoto oscillator and the accompanying mathematical analysis. For example, what is one to make of Kuramoto's assumption that R is constant? The theorem must be something like this. For most initial conditions, for most realizations, and for large fractions of the time, R over time stays within a certain degree of the constant. It's an open problem to make this precise. So there's some precision issues with these models. This issue could be difficult, as Nancy Copel pointed out. It may be connected to questions about the foundations of statistical mechanics, irreversibility, Poincare recurrence, etc. So these are all kind of these issues in complexity theory that have to do with dynamics. And so, there are a lot of open questions in terms of looking at oscillators that are coupled and uncoupled. And so there's a lot of kind of fertile ground for this. So after 3 decades of research, the study of mutual synchronization is prospering theoretically, but like many branches of mathematical biology, it has wandered too far from its source. There is no serious confrontation between theory and experiment. We need to follow the example of 2 related fields, excitable media and central pattern generators. So the theory of excitable media has developed alongside experimental work on spiral and scroll waves and the Belousov-Zhabotinsky reaction. Similarly, Ermentrout and Kopel's theory of phase locking in chains of oscillators has been directly motivated by experiments on the central pattern generator of Lamprey and has led to some surprising predictions that were recently verified by their experimental collaborators. But I suspect that mutual synchronization is going to be co-opted by physics, where the oscillators are closer to those imagined in their theories. There have already been some exciting applications to charge density waves into arrays of microwave oscillators and superconducting Josephson conjunctions. On second thought, perhaps co-opted is not the right word, since mutual synchronization began in physics with Huygens' discovery of phase locking between two pendula hung on the same board. And so they talk about theory here, and they talk about sort of how one can use oscillator networks to compute, learn, or recognize patterns. This subject should appeal to people caught up in the current excitement about neural networks. Abbott, in 1990, has taken a first step in this direction. So this is an oldish paper. I didn't know how old it was. The recent observation of stimulus-induced synchronization in the visual cortex has spawned several theories involving oscillator networks. Though there's still uncertainty about the biological significance of the experimental observations. But in any case, Norbert Wiener would be pleased to see that we're thinking about oscillators in the brain again. So that's that paper, and that's that topic. And I think there's this link between Wiener's work in his career. Some of that was a cybernetics influence, and some of it was more sort of the signal processing aspect of his work. But, how these ideas can kind of transform themselves in entire fields of study. So did we have any follow-up or questions on that?
Certainly interesting about the EEG.
Yeah. That you'd be interested in that.
It did make me wonder. I mean, as well as some the additional comments that they made about Wiener's work, or kind of lack of citing or things like that. It's something that came up in the complexity discussion was. I think it was talking about who was it? I forget the other person, but there was just like we coined, we wanted a different word than cybernetics because we just didn't want to invite Wiener.
It was about artificial intelligence itself, I think, right?
Yeah. And it was
they wanted to avoid Wiener.
We wanted to avoid Wiener. And I wonder, I'm starting to get this feeling like he's a little Buckminster Fuller-ish, he's got good idea, like he seemed to be everywhere. He was certainly influential.
Yeah.
But at the same time, I should check if Carl Prubram's book is if there's an ebook now that I can search for terms and things like that. I wonder if he's got any good Wiener stories that we can share.
Oh yeah.
Because he was certainly invited to a lot of those meetings, and definitely got to work with him, or I would. Yeah. Anyway, I'll see if I can find some stories.
Yeah, that's great. Yeah, I thought you'd be interested in the whole brainwaves thing. But
Oh yeah. I mean, this is I've got to figure out if that was something he was doing with Carl.
yeah. Yeah, I don't know. I just ran across this paper, but it looks interesting because I wasn't aware. I know that Wiener had done a number of papers on signal processing and random processes and things like that.
For sure.
Yeah.
For sure.
So I'm not sure about that figure one. I mean, like I had mentioned, it looks kind of like a wavelet, and I don't know if there's a connection between that.
I can't see your screen though.
Oh well, I didn't. Let me bring it back.
Okay.
So, figure one. So this is figure one here.
Oh yeah. No, I see what you mean.
Yeah. So I mean, like, I don't know if you think that looks familiar to you or what you had to say about that.
What's the? Sorry, I'm seeing this on the. Oh, this is his. Interesting. I mean, it's so hard to know because like certainly given the time, like I mean that doesn't make sense initially, right?
Yeah.
In that what we think of as full spectrum these days, looks more like a power law behavior,
Yeah.
so it's high power, low frequency, going off, going down, and then there's a little peak out of that at around 10 hertz, and then maybe like a smaller one at like 15.
Right.
So, but at the same time, like given the amplifiers and like maybe what you're using as your high pass filter,
Right.
Yeah. I mean, like again, like that could be because of like sort of some artifacts of the signal analysis that they're doing, but
Yeah.
like again, like were they even doing signal analysis? Like,
Well, this is a
it would have
schematic
all been
sketch.
going through electronic. I mean, like it would have literally been analog circuitry, right?
Yeah.
I mean, there's no DSP in this case.
Right.
Is what I'm saying. But I'm just not good enough to know, that era is electronics. Like if that's what, maybe if that's what he was kind of focusing in on.
Yeah.
But it doesn't look natural.
Okay. Yeah. So it's like I don't know. There's I don't want to say scientific fraud, but the kind of thing you would say if like.
It's like if you can draw your own results.
Yeah.
Yeah. Let's give him the benefit of the doubt, and he saw something around 10 hertz because
Right.
like even Berger did in the the late 20s,
Yeah.
right? So it certainly should have been possible.
Right. Well, I think the point of figure one is it's a schematic. Like this is the typical thing that you would see, and then to go on to make theoretical statements about it. So it's not like it's like the typical thing, and of course, there's probably a lot of variation there. So
yeah.
But
sure.
I like how Sturgatz leads it to like a lot of the synchronization work. So like basically that is leading you to these models of synchronization. It's explaining some of the features of synchronization. And of course, in synchronization work, you won't just find like this archetype, you'll find like a lot of variation in the behavior. And a lot of times in complexity theory, we distill that down to like some like a power law or something. And we can describe it with that, but the actual plot is not, it's not idealized. But we assume that that's the theoretical model because we can describe it with a mathematical equation or something like that. And so then we also assume that that's universal, that you can go across different systems.
Yeah, for sure.
Yeah. All right. So yeah, looks like Jesse had to leave. So I think that's all for this week. Thanks for attending. See you next week.
Thank you.
Thank you.
Yeah. Talk to you. See you Monday.
See you next
Yeah.
week.
Yeah. See you next week.